Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal sab changa si? I hope that you guys are doing good. Although this entire video we have discussed in the live bi-weekly contest 105, but still we have to make a proper video on top of it. So yeah, this video is for that reason only. So the question simply says, again, greatest common divisor traversal. So we know for sure after reading that some math logic will be involved. Either it can be straightforward GCD function, or maybe something beside or something inside that GCD function. Let's see. So basically it says that we are given a zero index integer I called as nums, and I'm allowed to traverse between the indexes I and j. Now when I say I can traverse, I mean I can index from traverse I and j such that indexes are not equal, which means I and j should be different, and also GCD of their corresponding nums value should be more than 1. Now GCD, it's a greatest common divisor, so that is that GCD between two numbers should be more than 1. See, greatest common divisor, if I have two numbers 4 and 8, or let's say if I have two numbers 4 and 12, greatest number which divides both of these, greatest common as in which divides both of these, and divisor, so it is 4. So that is the reason how you can just, let's say if I say you 6 and 8, greatest common divisor which divides both of them is 2. So this actually means that your greatest common divisor should be, again, 1 is a number which divides everyone, so it is saying please have it more than 1. Now it says that my task is to determine it for every pair of indices I and j. So I have to go and try for all pair of indices. Now first question for you is, pause the video and tell me how many pair of indices are there in an array. There are n square pair of indices. So if I have I is less than j, again I is less than j, I will have roughly n square pair of indices. Now for every of those pairs I have to tell if they are following this condition or not, and there exists a sequence of traverse that can make us from I to j, and it is not that from I to j I can directly go. It is not saying that any sequence of traversal which can land me from I to j. I'll tell you what that any sequence of traversal means, but yeah, I have to go on. I'll take all the ij pairs, and I want to go from index I to index j by traversing any values. I should ultimately start from I, reach to j. That is my aim, and I want to reach to all indices, to all pairs. Right now I have to return true if it is possible to traverse between all such pair of indices, or false otherwise. Now one very basic way, 2 3 6, one very basic way, as you know, you have to go and try for all pair of indices, which means if I is here, then j should be here, and if I is here, j should be here, and if I is here, my j should be here. These are all the pair of indices, which means 3 pair of indices in this specific problem. But Aryan, you said n square pairs, bro. You know what I mean by n square. That is a simple for loop. I to j and I to n, and j is from I plus 1 to n. Now for this specific pair, or let's say for this pair, let's say one pair was I to j, right, if you remembered. So for this pair you can easily see that these are connecting. So my I and j are, when I is less than j, for sure there for it the GCD value will be more than 1. So I can use maybe a function underscore GCD to get the value of nums of I and nums of j, and by that I can get to know if they are connecting or not. Bro, that is great, but I want for all the pairs, which means I'll go on to this value also. But this I can see that GCD is not 1. So shall I say that I cannot find between all pair of indices? So the answer is no. Because it says that I can choose any sequence of traversal, which means I just want that GCD between these two, which means these two should be connecting. These two I and j should be connecting. I have to determine every pair of indices I and j where I is less than j, and there exists a sequence of traversal. Ultimately I want that these two I and j should connect, so any sequence of traversal which connects them will be good for me, and traversal which connects them, as in traversal, will only be applicable where the GCD is more than 1. So I can easily say 2 to 6 I can connect because I know the GCD is more than 1. 6 to 3 I can connect because I know the GCD of 3 and 6 is 3, which is more than 1. So I can say from 2 to 6 to 3 I can connect, and I can ultimately say 2 to 3 is actually my good I and j pair, because I can, a sequence of traversal I can reach my 3, which means I can reach my j from my I. That's, I can say that okay, INJ it's actually a good pair. And again, if you know that last pair meaning INJ, they for sure are directly connected, so it's a good pair. So one very basic thing is, one thing you are doing in your approach is you are going on and trying for all the IJ pairs. So for sure it will be O of n square, which will for sure not work. Now after that, you also got to know, even if I go and try for I and J pairs, still there can be a chance that they are not directly connected, which means there's a lot of wording coming in connected. They should be directly connected, indirectly connected, which means I made a connection from 2 to 6 and then made a connection from 3 to 6, and then I was saying I was able to reach from 2 to 3, thus I can say they are connected to each other. So whenever this connection comes in, oh, connected nodes, kind of we are putting some edges they, and we are trying to find if they're connected or not. So maybe we can use graph. Now in to just know if something is connected or not, we primarily use DSU. So there's a high chance that you end up thinking, okay, maybe I can apply some DSU logic. Again, disjoint set union, DSU, if you have not watched, go and watch previous days video in which in that I explained the application of DSU, and there are a lot of videos in the channel for DSU itself. Now, so one thing again, the one, and I'm not saying that we will use DSU in this, but I'm saying the intuition, the wording itself defines that what we can use. So by this, if I want to know if two things are connected or not at any point of time, I can use a DSU for that. But ultimately I want that all the pairs should be connected, so maybe I can use something else also later in future. But yeah, one thing I have told you so far, that okay, maybe these things we can use. Now coming on back, that okay, for this we got to know the GCD is 1, so maybe we try to find some indirect connection, which means from 2 to 3 and then 3 to 6. So we ultimately got to know that we want all pairs to be connected to each other, which means okay, it was 2, 3 and 6. So we wanted my 2 to 3 to connect to each other, my 2 to 6 to connect to each other, and then I wanted my 3 to 6 to also connect then I also wanted my 3 to 6 to also connect with each other. So ultimately, can't I say that I want all of them to be directly or indirectly connect to each other, right? So even if I remove this, specific edge, still I am saying, right, 2 to 3 can connect. So I just want every node, every value should directly or indirectly connect to each other. That is primarily my aim. Now my aim has reduced to that, okay, rather than trying for all the pairs, I just want that, okay, please give me any specific connection in which I can for sure say that all nodes are directly or indirectly connecting to each other. But Aryan, how will you prove that all nodes, again, you can know that a few nodes are connected to each other, but all nodes are doing that or not, which means okay, if I just simply make the connection out, let's say my 4 is connected to 12, my 4 is connected to 8, my 3 is connected to 12, then I can say, right, all of them are connected to each other because they are in one single component. So I can ultimately say, if I made the connection and after making the connection, if all of them are residing inside one component, which means all of them are directly or indirectly connected to each other. And if something is directly or indirectly connected to each other, which means I can easily go from 3 to 8, I can easily go from 3 to 4, I can easily go from 8 to 12, I can go from anywhere to anywhere because I just want any sequence of traversal inside this graph, and it is connected graph, so for sure I can reach anywhere possible. So now my aim is, okay, I will just simply build some connection, and ultimately in the end I just want to know if my entire graph which I have made, again, I am building the connection between the nodes, so for sure I can infer that as a graph, and ultimately I want that ultimately in my graph should have one connected component, which means for that component, number of nodes in that component should be my n. If that is the case, number of nodes in that component are n, I can easily say that graph is connected. So although earlier here we saw that, okay, we had to connect and want to know if it is in one component or not, then we realized, bro, ultimately in the end, after making all the connections, I can ultimately in the end check by doing a simple DFS traversal that all the nodes in my graph are in one component, which means I can do a simple DFS traversal and count the number of nodes in that final component. If the number of nodes are n, which means all the nodes are connected to each other in that component, and bro, that is it. I don't, or I might not need a DSU in this case again. So we thought of that, okay, intuition says DSU, but then ultimately what our maqsad was, because we don't have to forget the maqsad, but ultimately our maqsad was that ultimately I just want to have one component, one connected component with n nodes, and that would be, if it is a case, then that would be my answer. So ultimately I just realized that I can just simply build the connections. Now Aryan, building the connections itself was a tricky part, because how would you know, okay, 4 to 3 you have to build the connection, 4 to 12 you can build the connection, of 4 to 8, which means are you again going on to all the n square pairs to build the connection itself from the actual nodes where you can build the, where you can have a GCD more than one? Are you doing that? If you will do that, Aryan, then the time consequence will again be of n square, which means to build a connection between 4 and 12, okay, by simply viewing, 4 and 12 can make a GCD more than one, but then in computerized thing you have to go and try, is 4 and 3 are having a GCD, is 4 and 12 are having, 4 and 3 was not having, okay, 4 and 12 was having, 4 and 8 was having, okay, great, build the connection. Then my 3 and 12 are having, 3 and 8 are having, no, okay, remove it. Then 8 and 12 are having, so are you saying that you will go on to all the n square pairs and then build the connection? No, that will still be of n square. So I have to think of a smart way to actually build the connection. Now ultimately building connection was based on the GCD of 2 values, and that should be more than 1. Now GCD, as I mentioned, is a greatest common divisor. If something is a greatest common divisor, which means I have some common divisor, and I can say divisor child is factor, so I can say I have some common factor between those two numbers, I and j. Now bro, if you want to find factors, or in general, or in, because see, factors are made up of prime factors, so okay, divisor, I can have the smaller term, the smaller part of that is factor. So I can say, okay, I can have factors. Now factors can be like 8 is a factor, okay, but I can just directly break it down to a prime factor, which is the most smallest unit of a factor, because I know that, okay, if the number is 8, I can have its multiple divisors. Okay, great. Then I can say, bro, simply hold on, you can simply find 8 and take the factors of 8. Factors of 8 can be 2, 2 and 2, right? 2, 2 and 2. Now again, I just want between two numbers, let's say 8 and 6, I just want that, what if even if I have one common factor, any smallest, I just want any smallest common factor which is more than 1, and we know prime factors, like as in prime numbers, are always more than 1. So if I can just say, bro, if I have 1 2 even and 1 2 any, I don't want the remaining 2s, that will not affect me. Even if I have a, let's say 2 2 2, let's say 2 2 3, let's say it would have been 12, 2 into 2 into 2, still I can say, okay bro, I just wanted one common factor between both of them, and that is more than sufficient for me. So I can simply say, bro, 2 is both, 2 is also in 8, 2 is also in 12, so for sure I can have one common factor between them. So what I did was, I can generate the prime factors and then see, okay, if it is common or not. Now comes the fact that for 4 the prime factors can be 2 and 2, for 3 again 2 into 2 4, for 3 again I'm just getting the prime factors for a number. Okay, for number 3 it is 3, for number 12 it is 2 2 and 3, for number 8 2 2 and 2. Now I told you that we don't require all the different, okay, 2 2 and 2, 1 2 is also enough. Like for me, even if I have 1 2 and any number, if a number also has one of the 2s, then I'm good to say I will have a common factor. So now the fact comes is, bro, how will you find these prime factors? That's a question. For that, efficiently to know the prime numbers itself, because it's a prime factor, so first term is prime number. So to efficiently know the prime number itself, please go and watch this specific prime video. Now when you have known this, you will simply, again, in this we have taught all the concepts related to prime, sieve, like segmented sieve, and other concepts also. But now we just have to find the prime factors. We can have a slight modification in the algorithm, and again, it's just a slight modification, that at every point of time you will keep the smallest prime factor while building the sieve itself. Now if you don't even know how to build a sieve, or if you just use it as a black box and you don't even know the logic of it, you will not be able to think of out of the box on how you can actually modify the Sieve itself. So I highly recommend go and watch this video. Now when you have watched it, so you would have seen the exact same image I have taken in the prime, this specific video also, while I was building the Sieve. In that Sieve, I simply told, okay, for the prime of 2, you will go on to I into I and then I plus like plus I plus I plus I and so on and so forth. So I am saying as you go on to as you go on to any number for the first time, okay, I go on to 4 for the first time, so I can mark for I'm going on the first time, I'm going on to that number first time. So for sure its smallest prime factor will be 2 because it was coming on from 2. So from 2 to I go to 4, then 6, then 8, then 10, then 12, then 14. So for all of them, okay, for 6 smallest prime factor is 2. For 8 SPF smallest prime factor is 8 of 2. Sorry, of 8 is 2. Smallest SPF of 10 is 2, and so on and so forth. So I'm just keeping track of the smallest prime factor for every number. Okay, bro, if it is 3, simply I into I for the first step. Again, if you are confused on why I into I, please go and watch this specific video. We have explained and proved everything with time complexity proof also. Now, coming on back, we can simply have a jump. So I can simply say, bro, SPF of 6 will still remain a 2. SPF of 6 because only the things which we thought of and we are overriding for the first time, where SPF value was not, or basically you can say if it was not marked as not prime earlier, then I will simply mark them first. So I'll simply say, okay, SPF of 9 is 3, SPF of 12 will not be overridden because SPF of 12 was already there too. So I will not override SPF of 12, I'll override SPF of 15. Now you can simply say, if I ask you, bro, what are the prime factors of number 12? So for number 12, you know, okay, SPF of 12 is 2, which means smallest prime factor of 12 is 2. Again, let's say while building the Sieve itself, you have populated this SPF value also. So for SPF of 12, it is 2, which means the smallest prime factor of 12 is 2. So what I will do is, I have a number 12, I will divide that with the SPF of 12 so as to get the next number 6. So you will see I'll jump on to my next number, which is 6. Now again, for number 6, SPF of 6 is again a 2. So SPF of 6 is again a 2. Now again divide. So I'll jump on to a number 3. Okay, I'll jump on to my number 3. Now for number 3, SPF of 3 is 3 itself. Okay, for 3, SPF of 3 is 3 itself. So I get a number 1. As soon as you get a number 1, please stop. By this you will get to know that you got the prime factors, which was 2, 2 and 3. And that's how simply you can get the prime factors of a number, by simply keeping track of the SPF, which is the smallest prime factor. So the code, as you have seen, of Sieve looks exactly like this. Okay, this is the code of Sieve, right? The condition which I have added is just SPF. So I initialize my SPF same as that of I initialize my prime. Now in the very beginning, I assign SPF of I to I itself, which means every number is there itself smallest prime factor. Now the exact same code of Sieve, the only line added is that if something is already marked as prime, which means it is not touched yet, please bro, put the SPF of J as I itself, and then simply keep on moving. Again, remaining code is exact same prime code, but you should be having a good understanding of how this code itself works, so that to understand that where actually to put this condition and what to put the condition as. Now if you have got the prime factor, so what you have got from here itself, now that from here itself you have populated this specific SPF value, but you saw that, okay, you also need to grab the actual prime factors of a number. For number 12, you have to grab the actual prime factors. So now you can have a new function. Now that new function, it will get in or take in a value x, and for that value x, he will tell me that, okay, its prime factors are 2 into 2 into 3. That can tell me this specific thing. Now it is my choice. Either I can say, okay, for the prime factor as 2, what is the count? It is 2. For the prime factor as 3, the count is 1. So either I can grab this portion, or I can modify this exact same function to grab only the prime factors, which means the unique prime factors, which means I can say, okay, the prime factors are 2 and 3, unique prime factors. Or I can say, give me all the prime factors, which means, okay, 2, 2 and 3. So I can modify this x, I can modify this function get factorization to get anything, either prime factors and their count, or the prime factors, all the prime factors, or the unique prime factors. In my case, I told you that I need only the unique prime factors because I'm only concerned that, okay, only one GCD common, only one common thing is more than enough for me. I don't want to make a big number or something like that. So I just want anything common will work for me. So what I did was I went on to all, like, I went on to my number until it becomes equal to 1, because you saw until it becomes equal to 1, I will have to keep on going. And when I say I'll keep on going, I'll simply say that you have a number x divided by SPF, smallest prime factor of x, and thus you will keep on getting the x. Now if you have the x, bro, simply keep on SPF of x says, okay, SPF of, if you remember, SPF x was, let's say 12 in the beginning, so SPF of x was 2. So bro, map says that 2's count keep on increasing. 2 is a prime factor, its count, okay, one time it has come. Then when x will become a 6, again SPF of 6 is 2, so again my 2's count will increase to 2. Then again it will become a 3, x has become a 3, so SPF of 3 is 3, so again map of 3 will become a 1. So this will keep the track of count of that specific prime factor. But ultimately I'm not concerned about the count, I'm concerned, again, I am showing you this specific code. I could have made it much smaller, I would have used an unordered set itself, but I'm showing you this specific code so that you can apply this logic everywhere, wherever required. These three are the conditions where you can actually apply the same function and modular and modify that according to you. So please make sure how to modify your Sieve. And again, this is the only modification which you might end up needing in CP itself, in your Sieve, which is SPF. And this is the functions which you can make for your factorization from your prime factors. Now we have got all the prime factors and their count. I just want all the unique prime factors, so I just iterated on my map itself and got the first value, which is the prime factor itself, which means all these unique values. I grabbed them and got, okay, I have got all the unique prime factors, and simply return those prime factors. Now coming on back to our actual main thing. So what we have done so far is that we went on and pre-computed the Sieve. From that pre-computation, now we know SPF of every number. Now what we can do is we just want some unique prime factors. So I will iterate on all the numbers, let's say nums of I, and then next nums of I, then nums of I, and then I'll simply call my get factorization function. But Aryan, the complexity will not be much, bro. You know the complexity of a Sieve is n log n. Now for this case, my n is maximum number, so I can say that let's say mv is the maximum value which I have taken, so it will be mv log of mv. This is the complexity of Sieve. If you don't know this, again I am saying please go and watch this video. In this we have proved it entirely. Now coming on back, so what is the complexity of this specific factorization? It is simply dividing my number by SPF smallest value. Smallest prime factor can be 2 itself. It can be smallest prime factor, right? So you can just imagine that every time I'm dividing my number by 2. So for sure, this operation is log of this x value to the base 2. Again, this is the maximum value which this function can incur, right? Okay, coming on back. So what we can do is we can go into all the elements n, and for every element, let's say if this is the maximum value itself, so this, to grab out all the prime factors, I will take log of max value time, which is okay for me, which is completely okay for me, because n log n or nearly that complexity will work for me. Again, n log n, see, max value is itself 1e5 and n is also 1e5, so it will work for me, no worries at all. Now when we have grabbed the unique prime factor of a number, now comes the part to build the connection. How will you build the connection? For sure, bro, whosoever have same or common prime factors, simply connect them, which means 2 and 2 can connect, 2 and 2 can connect. Oh, so I should be actually again knowing that, okay, 2, wherever I have 2, all these nodes can connect to each other. Okay, so what I can do is I can reverse this mapping. Right now mapping is from your ID to all the prime factors. Now I will reverse it, which means I will keep, okay, from prime factor to the IDs itself. So for the prime factor of 2, IDs of 0, ID of 2 and ID of 3 are the numbers which I have to build a connection for, which means I will have to connect them. Now when I say to connect them, the first thing which should come to your mind is DSU. Because it is very easy to connect numbers. But in this case, we can see, we just simply have to know if we just connect them all three, if we just connect all three of them, then my work will be done. So I can simply say, now I can connect 0 and 2, I can connect 2 and 3. That's a simple connection, just a simple, okay, go on to I and connect with I minus 1. go on to I, connect with I minus 1, and that's how I can build a simple connection. So not only with DSU but also with a simple graph or simple DFS, you can connect them also. So I'll just simply connect them, say okay, 2 and 0 I can simply connect, make an edge. Okay, 3 and 2 make an edge. I'm making an edge between their indexes itself, because it's a unique identifier. Now, okay, for the prime factor of 3, I can simply know that, okay, it is of 12 itself. So I'll go on and say, okay, prime factor of 3, wherever 3 is there, it is at the index 1, it is at the index 2. Okay, bro, simply now build a connection between them also. So what will happen when I say build the connection? You will see that 0, 2 and 3. 0 to 2, I build a connection. 2 to 3, I build a connection. And then 1 to 2, I again build a connection. Now I have built this specific graph. Just ultimately go and do a simple DFS traversal, because it's just, it can be multiple components also. It can happen that, okay, I have another component, but if I do a simple only once, if I do a DFS traversal, then it will go on to either one of the components and will go and traverse the entire component and give me the size of the component. If the component size is n, then I know it is just one component. If the component size is less than n, I know it is a separated component. So I will not have to use a DSU. I'm not saying DSU is a bad thing, but DSU has a bit big code rather than a DFS code. So DFS code is much more short and simple. It's the reason you should be having, again, in an interview, you don't have that much time to even apply or implement your DSU function, because in that, most optimal DSU is DSU by rank, right? So, and we have already covered that, but in this, I'll recommend that you just want to know the component. Okay, the component size is n, which means all the n nodes are connected to each other in just one component. So if ultimately when you have built the graph, just check if the component size is n. So now it will be, you will simply say that's, if the existence size is n, simply return a true. Now the code is pretty simple, exactly same as in the very beginning. You can have a Sieve function, you can have some global variables, although you don't need it. You can also call it again and again, but this can be used in cases when you have to do some pre-computation and you don't want to call the test cases again and again. I will show you a slight modification or improvisation in this code, in which by which you can hack kind of Leetcode test cases, because Leetcode is not good when it comes to multiple test cases. I'll tell you what it means. So firstly, okay, you will have a Sieve, and then you saw that I have a prime factorization, which will actually accept x and give me all the unique prime factors. And I show you, okay, it is maximum value log of maximum value, and this log of maximum value, which is just time it is taking. Now I will actually come on to my main function, which is actual main function. Now as you can see, for all the test cases, I am calling this Sieve function. Now as you know that Leetcode kind of works like that. Okay, let's say if I have a test case like this, again, there are different test cases. So Leetcode keeps this entire thing in the cache itself. So what you can do is you can have a small check. Again, I will not recommend this in actual, see, the code forces by default, every test case is very fresh, but in Leetcode it is not true. So one improvisation, which again, this is not for this question, it is for contest itself, which you can do in future contest where you do some pre-computation, is that, okay, see if you will see it, it will be calculated every time a new test case is called. But you know that, okay, your Sieve function is more than enough to be called once. So what you can do is, you know, by default, your prime value will be true for everyone. So so you can just simply say that, your prime value will be false for everyone by default. So what you can do is, one thing very basic, say that if your prime value, which means if my prime of, let's say, any number 2, if it is actually equal to false, then simply do a Sieve for the first time. This you can actually do that, okay, it will do a Sieve for the first time and it will not repeat the Sieve again and again. By this you can have some improvisation which you can actually utilize in the contest, but I will not recommend, because this is how Leetcode functionality is, which is not good. Now coming on back, that we will now know that we have to get for all the indexes I, what are all the prime factors. If you remembered, I want to know for the index I, Okay, where it is gone. For the index I, what are all the prime factors it has? Prime factors it has. Now, when I have grabbed that thing, okay, for the index I, what are the prime factors? Now reverse it. Reverse map I will make. Okay, for the prime factor, what is the indexes it can have? Okay, so I'll just say for the prime factor, what all indexes I can have. I'll iterate on the entire map which I have grabbed from here itself, and then from that map I will just do a reverse map. Okay, for the prime factors, what are all the indexes? Again, for your simplicity, I have split it into 3 conditions, but I can club them into one condition and make the code much more smaller, but then it could have been a bit harder for you to understand. Coming on back, now we can build the graph. Again, if you remember, building the graph is on top of, now we know that we had made a reverse map. This is the reverse map in which prime factor to actually all the indexes. Make a map, sorry, make a graph on simply saying go on to all the values of your map and then build a connection I and I minus 1, I and I minus 1, and so on and so forth. So I'll simply go on and iterate on the entire reverse map here. And okay, what is the entire vector? Simply make the edges, which means make an edge from id of I minus 1 to id of I. Make an edge and make an undirected edge. I'll make an undirected edge between them. And again, if I had just one node, so the edge cannot be built, so you can simply continue. But if you have 2 or more nodes, simply keep on making the edge. Now again, for this you can see it is same. You can have how many number of prime factors, and for that how many number of different node values. Node values can be n, and prime factors, as we saw, that for everyone can be log mv, which is log maximum value. So for sure in this also complexity is O of n into log mv. Same for this also, O of n into log mv, and same for this also, O into n log mv. Now coming on back, when the entire graph is built, simply do a DFS traversal. I'll simply call a DFS traversal with a count variable. Now this count should give me count of that. Again, I'm calling DFS just once, so it will go and traverse any component in which starts from 0, and that should actually grab me the number of nodes in that component. So this DFS traversal, it will just start off and say, bro, simply keep on visiting the node, simply increase the count as you visit some node, and simply visit its neighbors itself. Simple DFS traversal. And as you know that it will simply keep on increasing the count. Again, it's a O of n time because it will simply a DFS traversal which will visit every node exactly once. With that, you will see that it will simply visit your entire graph or entire component if the component size is n. If the count is n, I can simply return a true because I know that this component connects every node to each other. So true, else simply return a false. And that's how you can simply solve it in O of n log mv in n O of n, because you can see mostly is O of n log mv, n log mv, n log mv, but here it is m log mv, where it is gone, mv log mv log of mv. But still this log of mv is actually kind of log of mv, like upper bound is log of mv. So you can say the time complexity is O of n log mv plus mv log mv. That is the complexity itself for this specific algorithm. But yeah, n and mv both are actually 1e5 itself, so it doesn't matter what you write. And space is also O of n plus mv. Mv for your prime factor, Sieve and stuff. N is for your another map, visited, and all that stuff. Again, I am saying this code can be made shorter. I can very easily club my Sieve and prime factors in one code. I can very easily club my these 2 conditions where I got the prime factors, I got and reversed the prime factors and map, and then I can simply iterate on the entire graph. And I can do a simple DFS traversal. Many things can be clubbed in this. So, but still, for your simplicity, I broke that in functions for you to use that in future. Cool. Thanks for watching. Goodbye. Take care. Bye bye.